In class, we introduced interpretations again. We'd already talked about them when we began discussing quantifiers, but now we're mainly going to use them as tools for showing that arguments are invalid. So let's begin by reminding ourselves what an interpretation is. It's really, in a certain sense, very simple. It's a set of things, a collection of things. Could be, as we say here, numbers, could be people, could be physical objects, could be the things in my pocket, could be all the students at the University of Maryland, could be any collection of things whatsoever, with one restriction. There's got to be at least one thing in the domain. We don't count it as a domain unless there's something in it. And once we've got our domain, then we get our interpretation by doing this. We'll have some predicate letters, the ones that we need for whatever collection of sentences we're interested in. For each predicate letter, we say which things in the domain the predicate letter applies to. So for example, if our domain was the set of all counting numbers, and one of the predicates was is an even number, well, the things that that predicate applies to would be 2, 4, 6, 8, etc., etc. Likewise, if we have names in the collection of formulas that we need to look at, we have to say for each name what it names, which thing in the domain it picks out. So for example, here's a very small example of an interpretation. The domain has 4 things in it, just the numbers 1, 2, 3, and 4. The predicate F is just applied to the numbers 1 and 2. And notice, by the way, that we don't always list this explicitly. That means that we implicitly know what not F applies to. It applies to all the other things in the domain. The predicate G, in this case, applies to the numbers 2, 3, and 4. And that means, once again, we know what the predicate not G applies to. It applies to the number 1. And in this case, the predicate H happens to be the empty set. That's okay. For example, there are no unicorns, but unicorn is a perfectly good predicate. And there are no numbers that are both even and odd. We could have a predicate that means is both even and odd. Well, that wouldn't apply to any members of the domain. That's okay. And in this case, not H would apply to everything in the domain. Likewise, when we go on to names, in this case, I've let A name the number 1, B named the number 2, C also names the number 1, and D names the number 3. We don't have to have a name for everything in the domain, and one thing can be referred to by 2 different names. That sometimes happens. So with all that in mind, what I want to do is go over a number of examples, several examples where we show that an argument is invalid by constructing an interpretation, by building up a domain, and by giving interpretations to the predicate letters and to the names if needed, although our examples here won't contain names, where at the end of the day we have a refutation of the argument. How do we refute an argument? Well, it's the same as it's always been. We present a counterexample. These counterexamples are abstract and formal, but they're still perfectly good counterexamples. There'll be interpretations in which the premises come out true, but in which the conclusion is false. That is, the denial of the conclusion is true. I say the denial of the conclusion because thinking of it that way is the useful way to go about constructing an interpretation. So we did some of these in class, but it will help to do some on our own. Before I go over this, I strongly recommend you take a crack at it yourself in each case, and then listen to my explanation. You may come out with a slightly different interpretation than I do, and it may work just as well. But you'll get the most out of this if you don't simply listen to me. You'll get the most out of it if you try to construct an interpretation on your own. So in this case, what we've got to do is we've got to build up an appropriate domain with appropriate interpretation for F, G, and H. So give it some thought, and then you can follow the explanation. Well, the first thing is that we want to list the sentences that need to come out true in the domain, and they are the 2 premises, and we list them explicitly here, but we could have avoided doing that. What's going to be more important is that we think about this conclusion in the right sort of way. We want the conclusion to be false. We want the denial of the conclusion to be true. That means we want what you get when you put a tilde in front of this conclusion to come out true. Now, that's fine, but the best thing to do here is first, in your mind, so to speak, make a quantifier switch by using quantifier negation. And then you can notice that the bit that follows the quantifier can now be rewritten. You know how to use not arrow. And so when we do that, what we'll have is this. So we want all three of these sentences to come out true in our interpretation. So our domain will build up as we go. We'll open the set bracket here, and we'll just start by putting something in the domain. I'm going to use numbers. I don't mean them to stand for truth values, and I'm not going to use 0 because that is likely to confuse the truth value issue. But I'll just start here with the number 1. Now, so we've got something in our domain, but where do we start saying what the predicates apply to? Well, the first thing is that when we build up these models, it's actually useful to have two lists here, one for the predicates on the left and one for the denials on the right, because as we go along, you'll see that sometimes it's better to think about the denial of the predicate. Back to our argument. We want to refute the argument by finding a case where all of these sentences are true, by making our interpretation fit that requirement. The best place to start then is where we can do something in one shot. If we put a GH into our interpretation, we know that this sentence is true no matter what else we add to the interpretation. So if we say that 1 is a G and also an H, then we're on our way. That means that this formula is true in our interpretation and will remain true no matter what we add. Why did we have the right to just say that G applies to 1 and so does H? Because we get to decide what the interpretation is. That's the point. We're trying to construct an interpretation that refutes the argument. And so we wanted our interpretation to contain something that's a G and an H. So we just said, okay, let's interpret the predicate G so that it applies to 1. Now maybe we'll end up adding other things that the predicate G applies to. Maybe we'll end up adding other things that the predicate H applies to. But so far, so long as the predicate G and the predicate H apply to the number 1, this formula is true in the interpretation. Now, the other formulas are all universals, and whether a universal holds is going to depend on what happens with each thing in our domain. We have to check for each thing in our domain that it fits the universal. But what we do at this point is we pause and we say, okay, suppose that the number 1 was the only thing in our domain. Suppose that was the end of the story. We haven't said anything about what F means yet, and we may or may not need to, but let's ask, if the only thing in our domain is the number 1, and 1 is a G and 1 is also an H, would this sentence be true, and would this sentence be true? Well, start with this one. If the number 1 is the only thing in our domain, then everything in the domain, all one thing, fits this description. Because 1 is a G, that means if 1 is an F, then 1 is a G is true. That's just how the truth table works. So if we stopped here, this formula would be true. For the same reason, so would this one. 1 is an H. That means that this description fits the number 1 because the antecedent is true if it is about the number 1. So if we stopped here, this sentence would be true. So we will do that. Now, in a full interpretation, we'd say what the predicate F referred to. And it's okay to go ahead and do that, but since all we're interested in here is constructing counterexamples, we know it won't matter. So long as 1 is the only thing in our domain, it doesn't matter whether 1 is an F or whether 1 is a non-F. In either case, all of these formulas will come out true. So this is enough to refute our argument. Okay, so in this case, the refutation was very easy. We have a domain with one thing in it and this very simple interpretation of the predicates. Carrying on. Here's another argument. It's also invalid. We want to show that this argument is invalid. So how are we going to do that? Well, once again, start by listing the things that we want to come out true in our interpretation. We want the first premise to come out true, the second premise, and this is the crucial bit. We want the denial of the conclusion to come out true. That means we want this preceded by a tilde. Once again, use what you know about quantifier negation. And use what you know about denied compounds. And in this case, if you remember the section from the book about denials of categoricals, what you'll know is that this turns into this formula here. This says some H or F. This says no H or F. And they are indeed the denials of one another. With that in mind, then, we start to build up our domain. We start to build up our interpretation. We're going to have to say what counts as an F. And we'll want to say what counts as a non-F, or we may. What counts as a G. And we may want to say what counts as a non-G. And an H. And likewise, we may find it convenient to list what the non-H's are. So, where do we start? Once again, we have an existential. Once again, so long as there's one thing in our interpretation that's both an F and a G, this formula will simply be true. There'll be nothing more that we'll need to say about it. So let's, this time just for variety, let's use the number 2. The number 2, we'll suppose, is an F and also a G. And that means that this formula is true in our interpretation no matter what else we add. Now, once again, we ask the question, suppose we stopped here. Suppose that our whole domain was nothing more than the number 2. And suppose that what we've said so far is all we've got. Would both of these conditionals come out true? If the answer is yes, then we're home free. If it's not yet clear whether they both come out true, we may need to say more about our interpretation. So let's start with the easy case here. If the number 2 is the only thing in our domain and that thing is a G, then this formula would come out true. That is to say, this sentence would come out true because this description fits the number 2. Since the number 2 is a G, it's true that if it's an H, then it's a G. If the number 2 is all we have in the domain, then this universal sentence would come out true. What about this one? Well, the number 2 is a non-F, and so we can't say that this applies to the number 2 by virtue of anything about the consequent. We also haven't said whether the number 2 is an H or not. So this one's left indeterminate. But we can specify whether the number 2 is an H or a non-H. We get to decide. And notice, if we decide that the number 2 is a non-H, then this formula will apply to the number 2, and if that's the whole of our domain, we finished once again. We have an interpretation where all of these formulas come out true. We've refuted this argument. Moving on, here's another argument. You might want to pause and see what you can do. In this case, as you'll see, it's a little bit trickier in this case. Things aren't quite so straightforward, but give it a try and see what you come up with. Okay, once again, we'll list the formulas that we want to come out true. We want both premises to come out true, and we want the denial of the conclusion to come out true. Well, the conclusion said some H or F, so what we know we want is for the denial of that, which is no H or F, to come out true. No H or F, of course, is this. So these are the sentences we want to come out true in our interpretation. Once again, we need a domain. We'll start building it up as we go. And we need interpretations for F. We may also find that we want to talk about non-F, G, non-G, H, non-H. The problem here is that whereas in the first two examples we had an existential, so we had something that could just straightforwardly get us started, in this case we don't. So what we need to do is start adding things to the domain in a way, if possible, that gets all three of these formulas to be true so far as we've gone. You might be able to see a way to do that. There's two ways, in fact. One way is this. Think about the consequence for each of these formulas. We have F, G, and H. If the only thing in the domain is, let's say, the number 5, and 5 is an F, and 5 is a G, and 5 is an H, then if that was the whole of the domain, if we stop there, then this would apply to each member of the domain, all one of them. This would apply to each member of the domain, and this would apply to each member of the domain. So that's one way that we can come up with an interpretation with only one thing in it. It doesn't always have to be one thing. There's nothing wrong with having more than one thing, but in this case we get off easy. One thing will do. Another way we could have gone here, and I think you can see that it will work equally well, is if we'd said not that everything was an F and also a G and also an H, but if we said that the number 5, which is our whole domain in this case, is a non-F and a non-G and a non-H. That would do just fine. This would be another way to get an interpretation in which all of these formulas here come out true. Now there are many, many other ways, but we have a counterexample, so we can stop. Could there be ways that had more than one object in the domain? Absolutely. You could have as many objects as you liked, but this will do. Here's another example. This one's going to be kind of the converse in terms of what's interesting to the one we just did. So take a moment, have a look at this, and see what you come up with here. Start by listing the formulas that you want to come out true. The premises, as always. And as always, the denial of the conclusion. By the way, You probably figured this out, but there should have been a therefore here because this is meant to be the conclusion of our argument. Well, the denial of the conclusion in this case, we may want to be a little bit more careful. We'll first do a quantifier negation. And now if you apply De Morgan's, you can see that this turns into not fx and h. And hx. So these are the formulas that we want to come out true in our interpretation. We're going to need a domain, and we're going to need interpretations for f, g, and h, or as the case may be, for their denials. Now, whereas in the previous problem we didn't have any existentials, in this case we've got an embarrassment of riches. We have three sentences that we want to come out true, and each of them is an existential. So we need something in our domain that is an f and a g. Well, let's let that be the number 1. Let's suppose that the number 1 is an f and also a g. So this formula is true regardless of what else we add to the domain. We also want something that's a g and a non-h, and if we wanted, we could let that also be the number 1. That'll do just fine, so I'll go ahead and do it. We'll say that whatever else we have to say about the predicate h, it doesn't apply to the number 1. So we've got 2 out of our 3 sentences coming out true. Finally, we have to look at this one. We need something that's a non-f and an h. Now we can see immediately that the number 1 isn't going to do because it's an f. So we add something to the domain. We add the number 2. We want the number 2 to be a non-f, but also an h. And so now this formula is also true in our interpretation. We haven't bothered to say whether the number 2 is a g or not. If you want to, you can go on and add that information, but it wouldn't change what matters, which is that whether or not we specify that, whether or not we say everything about our interpretation, we already have a refutation of this argument. We already have an interpretation in which the premises are true and the conclusion is false. The premises are true and the denial of the conclusion is true. But here's a case where in order to get the refutation, we had to have at least 2 objects. It was forced on us. One more. This is a simpler argument in some ways because it only has 1 premise and it only has 2 predicates, but it introduces something new and something that we didn't actually get around to talking about in class. So here we want our premise to come out true, of course. And we want the denial of the conclusion to come out true. Here we better put in some parentheses. We're going to slip our conclusion in here. So we want both of these to come out true. But notice, this is not a quantified formula. This is, this isn't. Furthermore, what we want to do is we want to take this formula that is governed by a negation and turn it into something easier to work with. If you use not arrow, you know that what we'll get is this. However, use what you know to make this part easier to work with. Not for some x gx is the same as for all x not gx. Now, we only have f and g. We're going to set up our domain as we go along. We only have 2 predicates to worry about. And we turn to our sentences at this point for some guidance on what to do. Now this case is sort of interesting. The first thing to notice is this. Whatever we put in the domain, it has to be a non-G. There cannot be any G's in our domain. This is a case where in order to get things to work out right, G is going to pick out the empty set. So that means that whatever we add here, it has to be a non-G, but that isn't enough to get us started. We need to add some object, let's just say the number 7, that makes no conflict with this and makes one or another of these things come out true. So we know that the number 7 is a non-G because otherwise we won't get a refutation of the argument. Now we also know that we need something that's an F. This conjunction here means that in effect we have 3 sentences that we want to come out true. We need something that's an F. Well, we can just let it be the number 7. Now we might ask, suppose we stopped here. Would this give us the refutation we want? Well, let's look here. It will if this sentence is true in the interpretation that we've constructed so far. Well, let's look. Does the number 7 fit this description? It does not, because the number 7 is an F and is not a G. So we need to add something else to our interpretation. So we'll add another object, the number 8. Or whatever you like. It could be Chester the magic horse. It doesn't matter. But we do know this, that the number 8 has to be a non-G, because when we've got a universal, each time we add an object, we have to come back to that universal and make sure that the object we've added fits what the universal says. It has to turn out that everything in our interpretation is a non-G, and so that must apply to the number 8. Now we don't need to worry about this. This is already taken care of. Doesn't matter what else we add, there's already something in the interpretation that's an F. And so we can just ignore that, but now we can go back over to this. We want to see if we can find a way to make our interpretation fit this requirement. We'd like the number 8 to fit this description. Now the number 8 is a non-G, so in order for the number 8 to fit this description, the number 8 would have to be a non-F. And now we've got what we want. Let's let this be our whole domain. We can see that everything in the domain is a non-G. We can see that something in the domain is an F, that's the number 7, and we can see that something in the domain fits this rather more difficult to say in English sentence. And so here we have our refutation. Here we have our counterexample. There are quite a few more exercises like this in the text, but this is a sampling of the kinds of things that come up when we're trying to refute an argument by constructing a counterexample.